In this video, we'll be talking about reference frames. And reference frames are really important because often we want to convert from one reference frame to another reference frame. We see these things in CNC machines and things when we've got a reference frame associated with the cutting head, reference frame associated with the thing that we're trying to cut. But we see them a lot in these robotic sort of systems as well. The basic idea of forward kinematics, we're reminded, is we're trying to get the position of the end effector in the reference frame of the base that we've got there. And each time a new joint is added to our system, we have another reference frame that's also added here. So for our diagram here, we'd have a fixed base, a reference frame associated with that. We'd have a reference frame associated with that first revolute joint that can turn like that. And then two more reference frames associated with each of those other joints. And then a final reference frame associated with the end effector as well. And so each time we add another one, the end effector effectively becomes further away from the base. So let's start with the most basic example where we have one joint. So we've got two reference frames here. One that's composed of x0 and y0, and one that's composed of x1 and y1. And essentially what we want to be able to do in forward kinematics is work out the pose in x, y, and z of the end effector, which is that square that we have up there, in the coordinate system of the base, in the x0, y0 coordinate system. Now, if we know L, where L is the length of that link between the joint and the end effector, and we know theta, where theta is the angle that the joint has moved through, we can use some basic trig, and by inspection it's pretty easy in this case to say that, well, x will be L1 cos theta 1 and y will be L1 sine theta 1. So it's very simple in this single joint scenario to actually calculate it directly using some basic trig. But what happens when we add a second joint on there? Here we're still trying to find the position or the pose of that box, but now we need to consider J1 and J2. And so we could use the law of sines and cosines to compute x and y, and we could use some vector maths. But remember, we need to be aware of those rotations that are occurring because we keep rotating and rotating through different angles. So it starts getting a little bit trickier. Here's what we'd be looking at. So theta is equal to theta 1 minus 90, which rotates us back, plus theta 2, which rotates us to the right angle that corresponds to the L2 linkage. We then, for x and y, it becomes a little trickier. So x is equal to L1 cos theta 1 plus L2 cos theta. And likewise, y is equal to L1 sine theta 1 plus L2 sine theta. And you can imagine as we add more and more joints, it gets more and more tricky. Particularly as some of those joints have twists and things in them. In our ABB robot that we've got here, we've got 6 different joints, and it'd be very difficult, although not impossible, to solve it in this particular way. So what we really need to do is come up with a better way to consistently solve these problems using some common terminology and a common process that allows them to solve it every time, regardless of the size of our joints or how they're positioned or how they're orientated against each other, or even the type of the joints, whether they be revolute or prismatic joints. Before we actually go through how we actually do it, let's go through some basic notation first. So what we're typically trying to do in forward kinematics is find the position of an object in a different reference frame, a different coordinate space. So we're trying to transform one coordinate space to another coordinate space. For example, we want to find the object A, the position or pose of object A in our reference frame 0. So we have a certain notation for this to make it simple for us. We say this is A0, where our superscript indicates the reference frame that we want the result to be with respect to. So A1 would be, which is also perfectly valid, is the position of A in reference frame 1, which is represented by x1 and y1. As we add each new link, it gets a new reference frame, and they're added, and we label them as L1, L2, L3 for each new link, and J1, J2, J3 for each new joint, and reference frame x0 and y0 and x1 and y1 and x2 and y2 and so on and so forth. We keep on incrementing as they go through.